All right, we are at 14.5, and we're going to go right into 14.6, the Doppler effect. So let's share the PowerPoint. And oops, I need to go back a bit. That's where we left off the last time, intensity levels and decibels. And here's a spherical wavefront. And whenever you have a point source of sound, where you approximate some sources of sound as a point source, and we see that there's a spherical wavefront that goes out in all directions, and the difference between R1 and R2 are you can imagine the R2 being the maximum of one wave, and R1 being the next maximum, so that there's lambda. The difference between R1 and R2 is lambda, the wavelength. So we can see that it radiates out in all directions. And the average power, or the intensity, is the average power divided by the area. Well, the area for the sphere, P average, is over 4 pi r squared. That's the area of a circle. So as r gets bigger, the intensity gets smaller. It reduces with it as an r squared term, 1 over r squared term. So you can see that the I1 is equal to P average over 4 pi R1 squared, and I2 is equal to P average divided by 4 pi R2 squared, so that the ratio between I1 and I2 is I2 R2 squared over R1 squared, so that the intensity level I1 is actually greater than I2. In other words, R2 squared, since it's a longer radius, is greater than R1 squared. And so it's diminishing. So that's why I1 is greater than I2 by the factor R2 squared over R1 squared. Okay, so if we imagine going further and further out, you can see how they show that the lambda is between this spherical wavefronts. As we go further out, the rays, those are the lines perpendicular to each wavefront, the rays get more and more parallel and become more and more perpendicular, so that if we're far away from the source, you can think of it as these planes parallel to the XY plane that are moving out at a velocity v, and the difference between the planes is lambda. Now we're going to use that when it comes to Doppler, and it doesn't even introduce, it goes right into Doppler. And I'm going to show a quick little cartoon, thanks to Walter Fent, very cartoonish, but you can see it. Now let's read the text here. As long as now what we have here is we have a stationary observer at the side of the road, and this is back in the old days when the sirens used to just be a single tone. Now there's all sorts of sirens. They're not just a single tone, but a single tone. You can think of it as a car horn. Like if somebody just pounces on their car horn and travels toward you, this is the same effect. As long as the emergency ambulance approaches the person, the intervals between the arriving wavefronts are shortened. So you think of these spherical wavefronts. So these spherical wavefronts are coming toward you, but so is the car. So there's a shortening of the wavelengths. And then look what happens when they pass the observer. So let's resume this video and count the flashes of the the observer as the wavefronts hit him. So we're resuming here, and you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's stop it there. So that was going, I don't know, I think it was more than 1 a second. Now watch when the ambulance passes the observer, and we'll count again. Now, this is a very exaggerated view, but it's just to get the point of the Doppler effect across. Okay, now let's count it at 1, 2, 3, 4, 5, and you can see that the wave fronts are spaced out, because not only do you have the speed of sound traveling, but it's being generated by a moving source. Now, the same thing happens if the siren were to be stationary and the fellow was on a bicycle or something headed towards the ambulance. And then you can get situations where both the observer and the source are moving either towards or away from each other. I don't know that I read the text. Now the vehicle leaves the person, so the wavefronts reach the person in longer intervals. But let's read the note. It says, this app is not very realistic in one respect. As the Doppler effect should be seen as clearly as possible, the sound waves have a smaller velocity than in reality. So the speed of the sound waves are very slow, just to get the principle across. So this is just conceptual, just to get the idea across. Okay, let's go back to the PowerPoint. Okay, so you have an observer on a bicycle with a stationary source. The observer is moving relative to a stationary source. So the velocity of the observer is v sub 0, or v of the observer. It's not a 0, it's an O, v of the observer. And the v is the source. The lambda of the source is, it's just lambda source. And the velocity of the source is 0. Now, so the additional wavefronts are detected, v0t divided by lambda s. So f sub 0, the frequency observed, is equal to the frequency of the source plus the velocity of the observer divided by lambda of the source. So if the lambda of the source is equal to the velocity divided by f sub s, then we get the frequency of the observer is equal to the frequency of the source plus v0 divided by v. So that's the observer moving toward the source. Now, the observer moving away relative to a stationary source, we can go through that again, and you get the frequency of the observer is fs v minus v0 divided by v. So it'll be a lower frequency. Now, the source is moving relative to a stationary observer. You have observer A and observer B. So lambda 0 is equal to lambda s minus vs over f. F of the observer is equal to v divided by lambda of the observer. So f of the observer is equal to v over lambda minus lambda of the source minus v of the source divided by frequency of the source equals v times frequency of the source divided by lambda of the source, frequency of the source minus velocity of the source. So lambda of the source is equal to v divided by the frequency of the source. F of the frequency of the observer is equal to v fs, the velocity times the divided by V minus V of the source. So the F of the observer is equal to the frequency of the source times V over V minus Vs. Now, in the general case, F sub 0 is equal to F sub S times the velocity, just the velocity in air, plus the velocity of the observer divided by V divided by minus V sub S. That's the general case. This isn't, I mean, it is listed in things to, this is 4.6. The Doppler effect is covered in the MCAT, so you should know at least this one, the general case. The frequency of the observer is equal to the frequency of the source times this relationship, the velocity of air plus velocity of the observer divided by the velocity of the sound in air minus the velocity of the source. And I think that does it for the Doppler effect. We'll end it here.